hope you took the time to work on the prerequisite skills. Recall from earlier in the semester that we learned that if you raise a base to a negative power, you take the reciprocal of the base and the exponent is positive. So that would come into play in B, C, and D, or you could remember what my beloved teacher, Mr. Hopkins, used to say, bring it downstairs, right? So this is 1 over 2 cubed, which is 1/8. I hope we're comfortable with things in A, right? Where we cube a fraction, we have to cube both the numerator and the denominator. And it should not surprise you, if you look at B and C, notice how the base in B and C, the bases are reciprocals of one another, right? So if the answer in letter B is 1/8, right, then this is the reciprocal, so that should not surprise you that the answer is 8. And again, following this rule, take the reciprocal of the base, raise it to the 4th, and we should get, let's see, that would be 81 over 16. And I work with the education students, and I always teach them to choose examples that are relevant to students' lives. So I think on number 2, this is pretty relevant. I think at this point, the coronavirus has a reproductive factor of just a little bit over 1, which means that one infected person typically only gives it to one other person. So that's how we've gotten the coronavirus at least sort of, kind of, a little bit under control compared to what happens when we have exponential growth. Although in some areas we're still seeing exponential growth. But anyway, if you filled this in and then you drew a diagram, right, we can see why all of the restrictions that have been put into place are such. Because if every infected person gave it to 3 others, which would probably happen if we weren't wearing masks and not holding large gatherings and all the social distancing we're doing, it probably we would infect at least 3 others, most likely, if we weren't taking precautions. So anyways, this shows that on day 0, we had 1 person with coronavirus. By day 4, we'd have 81. Certainly very possible. All right, so then what function did we just show? All right, and we have found an exponential function. And sometimes we use like exponential growth, like we use it almost like as a slang term, like, oh my gosh, my stress level is like growing exponentially here, right? So we have some sense of what exponential growth means. But what we just found is the exponential equation 3 to the x. Okay, so by day 4, we did 3 to the 4th power, and we can see the 81 circles there if I had drawn those all out. So an exponential function, by definition here, mine looks a little fuzzier than yours on your paper because I enlarged my paper and it stretched a little too much. But anyway, with this definition of exponential function, you always want to look at the fine print in a definition or theorem. And the fine print tells you, you get this definition of like, well, this is when this is true, but the fine print says, oh, but as long as this doesn't happen and this doesn't happen. All right, and I equate that to like the fine print of a coupon, right? And I don't know if I want to take the time to tell you my whole story about how I hate coupons, because coupons come in the mail all the time. I always shove them in this one drawer in my house, and then they all expire, and then I throw them out. And I don't really know why I do that. I just feel like I should hang on to coupons. But the thing that I hate about coupons is I don't really think they save you much money because there's always stuff in the fine print. All right, so if you get something that says like free sub, okay, in the fine print, it probably says free sub if you buy a bag of chips and a soda and a cookie. And by the time you buy all of that, and that's so overpriced that you might as well have just paid for the sub in the first place. So our math theorems have the same type of fine print, right? So a coupon, you might get like 50% off, but it's only valid from 12 to noon, right? And so you think you're getting this great deal, but there's some fine print. So with exponential functions, what we have to notice in the fine print is that a cannot be, first of all, a can't be 0, a also can't be 1, and then a has to be greater than 0. So I'm not talking about raising negative numbers to a power. All right, so we are only looking at, so greater than 0. So I could raise something very small like 0.01, right? That's greater than 0. That's a possibility. Or, 2 to the x, 3 to the x, and so on. So an exponential function can represent growth. All right, so we've got the coronavirus, or it could also represent decay. All right, because think about taking 0.01 and raising that to like the fifth, right? And look what happens to that. Try that on your calculator. You'll notice when you raise that to the fifth power, it's a very, very small number. Okay, so raising a number between 0 and 1, right? A fraction, a proper fraction, I should say, when you raise it to a power, for example, like if I take 1/2 and I square it, right? Squaring usually makes things bigger, right? But not if I square something like 1/2, I get a quarter, which is actually smaller. Okay, so if I raise a proper fraction to a power, I actually get a smaller answer. So that's where we get this idea of like exponential decay. So think about half-lives from chemistry, right? Where if you have half of a compound left, and then say every 5 years it decays and you only have half of what you started. And what's kind of interesting about looking at that, like if I drew that on a blank piece of paper, okay, here's an amount that I have left, then I only have half. Okay, so this amount is gone. Okay, then I only have half. Then half of what's left. Half again of what's left. Notice, am I ever going to get to 0? Right, if I keep taking half, so I have less and less left over every time. But eventually my pen's going to get too thick to keep going any further with this. But am I ever going to get to 0? Right? And I'm not, which means that I can never get an output of 0 for one of these exponential functions. Right? So that's going to help me when I talk about range and domain. So let's go back here and look at some examples. Okay, so we've already talked about the function y equals 3 to the x. And if I were to plug in 0 for x, anything to the 0 is 1, right? That means that every single exponential function, right, whether I'm talking about a base being a value greater than 1, or whether I have a base that's a proper fraction, which is less than 1, no matter what my base is, anything to the 0 power is 1. So every single exponential function ever, no matter what base, goes through this 0.01. All right, and then I can input anything, right? I can input positives, right? I did this with the coronavirus example, but 3 to the negative first is 1/3, right? 3 to the negative second is 1/9, but I am never going to get to 0. So I actually have a horizontal asymptote line for these functions at y equals 0. Okay, so I will get closer and closer to 0, just like what happened over here. I get closer and closer to 0, but I never actually achieve 0. And if I look at something like, let me change colors in green, if I do y equals 5 to the x, right, that's going to get bigger faster. What's kind of interesting is it'll be above this curve over here, but then it's actually below the curve down here, right? Because 3 to the negative first is 1/3, 5 to the negative first is 1/5. It's less. Okay. Or if I have something like 1/2 to the x, right? If I input a negative, that would take the reciprocal of the base. If I input a negative for x, I'd have to flip that base. For example, 1/2 to the negative third, as we saw stuff like this up in the warm-up, that would be 8, right? So over at -3, I'm at 8. All right, but then if I raise this to the second, I'd be at 1/4. Okay, so any exponential function where the base is between 0 and 1 is going to represent decay. Okay, so a is between 0 and 1. I get this shape, right? And then anytime a is greater than 1, I get this shape. And if I were to look at, say, let me change colors, y equals 1/5 to the x. 1/5 to the x, again, it goes through this point, and it would be less over here, but greater over here, right? Because 1/5 to the negative third would actually be 125. Okay, so it's greater on that side. So this says, what's the domain of all exponential functions? So I can input for x. Some of you might be thinking, wait a minute, you just said can't be negative, can't be 0. That's a, right? That's a, the base. Okay, but how about x? X can be anything, right? X can be negative, right? I've got all these values. X can be negative, x can be 0, obviously x can be positive. So my domain is all reals, and then what's the range? What kind of output am I getting? And I said, okay, I've got a horizontal asymptote line at y equals 0, and therefore my range is 0 to infinity. So in example 5, we are given the graph of y equals 3 to the x, and when x is negated, how does this reflect the graph? Right, and so again, we did work with this earlier in the semester. If I negate the x, right, meaning that here, if x is 1, right, and I get this certain output of 3, if I negate the x, then that means at -1, I get that output. So what I'm doing then is I am reflecting the graph through the y-axis. Right, because the output at -1 is now the output at +1, or vice versa. And so that's why it should make sense to you that 3 to the negative x is the same as 1/3 to the x, right? We know that from our rules with exponents. All right, so let's take a look at the inverse. So another thing we learned already is that, and there should be a y here. That's a typo. It's missing a y. So let's find the inverse of this function both graphically and algebraically. And I have to go to the next page for mine. Okay, so here is the function y equals 3 to the x. And one thing that we know about inverses, so to do it algebraically, you just switch the x and the y, which this looks really weird. We don't like to have equations that look like this, right? We always want our equations to be in the form of y equals. So we'll address that in a minute. right? But if this is the point when we reflect through the line y equals x, remember we take the x and y and we switch them. So this is the point over 0 up 1. This is the point up here, 1, 3, which means then I would have the point 3, 1. And I'd have this point. And we have learned that when reflecting, right, think about taking this graph, folding it over this line, and the two halves would match up. Okay, so this is a graph of the inverse of y equals 3 to the x. And so what's this called? Right, what's the opposite? What undoes the exponential function? And it's defined for you on the next page, but the inverse, if I were to solve this for y, this would be log to the base 3 of x. So the inverse of an exponential function is a logarithmic function. And the domain and range have to switch also. Okay, so the domain of, back in number 4, the range of the exponential function becomes the domain of the inverse function. So I can only input, for a logarithmic function, I can only input values greater than 0. Can't input negatives, can't input 0 itself, but the range would be all reals. And the simplest way to define a logarithm, you know, if you said to me, what is a logarithm? A logarithm is an exponent. Right? The logarithm is what is the exponent that I need to raise a fixed number, a base, right? What's the power I need to raise that base so that I get a certain output, a certain number? So let's do one of these examples together, and then I'm going to ask you to work on them yourself, by yourself. Actually, I don't want to go to my next page because I already answered them all. But let's look at this, right? And the first exercises just say, write this in, write this as a logarithm. Right? So when I do that, the base, right? 2 is my base, so that's the little number here. That's the base, and the answer is the exponent. So I would read this log base 2 of 64 equals 6. All right, and then there's a few equations down here asking you to solve for x in number 9. And so you want to do the same thing. You want to write them, take the equation that you're given, like you're given this, write this in exponential form, and then solve for x. Okay, so the little guy is the base, the exponent is the answer. All right, and so this would really say 3 to the 4th equals x, and then 3 to the 4th is 81. All right, so stop the video here, work on those exercises in 8 and 9, and pick back up in the next video section.